Welcome to this third tutorial in the mini-series on trigonometry at the higher level. And here I'm giving a derivation formulae. So this is definitely optional. I don't think you need to know how to do these derivations, but there'll be many of you who, when you see the addition formulae from the last tutorial, will say, but where does that come from? And so this is going to be one way of proving it using some geometry. And in fact, what's sort of nice about this derivation, I don't know if it's the standard derivation, it's just something that I came up with the other day, but it does utilize the full range of trigonometry that you learn at the higher level. So that's kind of nice in the way that you see kind of combining the sine rule and the cosine rule and so on and so forth to derive these addition formulae. I should warn you at the outset, it's not straightforward derivation. This is not going to be the most straightforward tutorial. But if you are, again, if you're curious where this thing comes from, if you have the patience to follow through this derivation, I think you'll find it quite satisfying to see, yes, indeed, we can, from basic geometry, prove those formulas. And I mentioned, if we just had a bit more maths, if we just had complex numbers are something that we knew, which is something that's normally covered a year later, there's a very, very beautiful derivation of those addition formulas that would take literally 2 lines. So that's kind of tantalizing. Perhaps that will act as a spur for many of you to kind of want to learn complex numbers in the future, because that's such a tremendous subject. But here we are, we're going to use geometry, and this is the construction that I want to use. I'm going to draw a right angle triangle. Okay, not too bad, that's a right angle triangle. And I'm going to choose an arbitrary point on this side and connect it to that vertex. There we go. So let me label this side as A. Let me label this hypotenuse as B. Let me label this other hypotenuse as C. And let me label this little segment of line here by Y. And let me label this side of the triangle here as X. So X takes us from this right angle up to this point, and Y takes us from this point to this point. And then I want to label our 2 angles. So here is angle A, and here is angle B. And it's going to be convenient for us just to list one other angle. We just need it briefly. I'm going to label this angle at the top here theta. All right. So that's lots of labeling. And now let us proceed. Well, first of all, what we want to know sine of A plus B. That's what the addition formula is going to be in terms of. Well, we can see straight away that sine of A plus B, which is this complete angle here, is A plus B. Sine of that would be the opposite side of the big right angle triangle divided by the hypotenuse. So that's going to be X plus Y divided by C. And similarly, cosine of A plus B will be the adjacent side over the hypotenuse of the big triangle. So it would simply be A divided by C. So that's fine, no problem. Now what our job is to find expressions for sine A, sine B, cosine B in terms of these various sides, and then basically find some clever algebra to relate those to these very simple expressions that we have for the sine of the of A plus B, cosine of A plus B, and we're going to somehow try and combine those expressions for the sines and cosines of the individual angles with these ones. And it will work, but it's going to take a little bit of patience, as we'll see. So let me do the easy ones first, you see, because I have one other right angle triangle here. So angle A is actually really easy. We have that the sine of A is in this lower right angle triangle. It's the opposite over the adjacent. It would just be x divided by b. And I have the cosine of A, again in that lower right angle triangle, is just the adjacent over the hypotenuse of that lower triangle, just be A divided by B. Very straightforward. Now you can see where all the trouble lies. It's angle B, because the top, or the upper triangle rather, is not right angled, and so we don't have any simple formulas for sine and cosine of B. However, we get to use the weapons that we learned at National 5, namely the sine rule and the cosine rule. So let's use the sine rule first. Remember, the sine rule says that the sine of this angle divided by that length will be the sine of any other angle in that triangle divided by its opposite length, and I'm going to choose the sine of this angle over that length. So we have that the sine of B divided by the opposite length, which is y, is equal to the sine of, I'm going to choose this angle, sine of theta, divided by its opposite length, which is b. So for that upper triangle, this is just a statement of the sine rule. But you notice that we can use the fact that theta is also an angle in the large right angle triangle to have a very simple expression for sine theta. It will be the opposite length in the big right angle triangle over the hypotenuse. So sine theta will be A over C. So this is A divided by C, all divided by B. And so I have a very simple expression ultimately for sine B. I say very simple, reasonably simple expression for sine B. Just multiply through by y, and I have A times y divided by B times C. Okay, so let me maybe underline these because we're going to use them. So we got this one using the sine rule. I'm being quite quick with my fractions here, so if you're slightly unsure with fractions, you might want to just do this a bit more slowly. But A over C divided by B is just A divided by BC, and then I'm multiplying that by y to get that. Now it gets tricky now because we have to use the cosine rule to get cos B, and this, to be honest, is going to be a bit messy, but just bear with me and we'll see how we get on. So the cosine of B we can get directly from the cosine rule, which is it's the sum of the squares of these two sides take away the square of the opposing side divided by twice the product of these two sides. So cosine of B is B squared plus C squared minus y squared, all divided by 2bc. That's fine. And I'm now going to do a little bit of playing around, essentially using various Pythagoras' theorems that we have hiding in here to get this as simple as I can. So the name of the game for the next couple of minutes is, can we get this much simpler? And we can, because you see there's obviously lots of relationships between these sides coming from Pythagoras' theorem. We have two of them. We have that b squared is a squared plus x squared. Pythagoras applied to the lower right angle triangle. And then for the large right angle triangle, we have that c squared is a squared plus the square of x plus y. Okay, so let's see, what do I want to do? I think the first thing I'm going to do is get rid of the c squared on top. All right, so let me try and fit that in here. I want to write, I'll tell you what I'll do actually. I'll just look at the numerator. that will be the best use of space here. So b squared plus c squared minus y squared. That numerator there, I want to write c squared as the sum of a squared and the square of x plus y. That's just using Pythagoras' theorem. So I have b squared plus, and then c squared is a squared plus x plus y squared. So I'll just put a little curly bracket there. That's c squared from Pythagoras. And then I have take away y squared. And you see this is quite nice. That y squared from expanding this will cancel that. So I'm going to have b squared plus a squared. And then I'm expanding out this square. I have x squared plus 2xy. And then plus y squared, take away y squared. Great, that's good. And then I can observe that, look, a squared plus x squared, I can use Pythagoras on the lower triangle, is just b squared. So actually these two together give me b squared. So I have two lots of b squared. So that's one lot of b squared, another lot of b squared, and then I just have 2xy. So that's really nice. That's really simplified a lot. And so I have a nice expression finally then for cos b. It's this expression divided by 2bc. I'm going to get rid of all the 2's, so divide top and bottom by 2, and I'm left with b squared plus xy, and then over bc. Good. And to be honest, that's the hard work all done. Now it's plain sailing. Right, we have expressions for sine A, sine B, cosine B, and we also have expressions for sine of a plus b and cosine of a plus b. We've simplified it as much as we can. Can we now relate these things together? So let's have a look at sine A, cosine B. What would happen if I multiplied the sine of A by the cosine of B? Well, let's see what we get if we do that. There's the sine of A. It's just x over b, and I'm going to multiply x over b by cos... Oh, sorry, I need to be a bit careful, don't I? When I say b, I mean the side b. So I'm going to multiply x divided by little b by the cosine of angle b, which is this expression. So I'm going to get x times this numerator here, which, let me just write that out, it's going to be x times b squared plus x times xy, which is x squared y. And then that is going to be divided by bc and also a factor of b from here. Alright, so I get b squared c. So I've just multiplied cos b by x over little b to get this. And then, let's see, what am I going to do now? I notice that from Pythagoras again, x squared is b squared minus a squared. Okay, so let me do that. Let me write, the first term is xb squared, and then the next term I'm going to write for x squared, I'm going to write b squared minus a squared. So I'm going to have b squared y take away a squared y, all divided by b squared c. And now you see some magic is happening now, because look, I've got these two terms have a factor of b squared, and the denominator has a factor of b squared, and so that's quite nice. This is b squared times x plus y divided by b squared c just gives me x plus y divided by c. And then the last term is just, it is what it is. It's minus a squared y divided by b squared c. And let's see if we can relate this to things that we already have. Well, what's very nice is that we see that x plus y over c is our sine of a plus b. That's good. And what about this term? Well, this is a over b times ay over bc. So if I multiply cos A by sine B, I'll get a squared y over b squared c. Hooray! That's lovely. I'm quite relieved actually that that worked out. So that's cosine A sine B. So what we've shown is that sine A cosine B is sine of A plus B minus cosine A sine B. And I'm not going to write it out because I don't have space, but taking this over to the other side of the equation would give me the addition formula for sine of A plus B. Sine A cos B plus cos A sine B. Perfect. And the reason I'm trying to be very precious with my space here is I want to look at the other one. So let's look at cosine A cosine B. So now I'm going to take my hard-won cosine B expression and multiply it by cosine of A. Cosine of A is A over B. So I'm going to have little a multiplying the top divided by little b multiplying the bottom. So that's going to give me ab squared plus axy divided by, and then little b times the bottom, so b squared c. This one I think comes out a bit easier, doesn't it? Because we see the first term, I have a common factor of b squared, it's just a over c. And then I have plus, just, it is what it is. It's axy divided by b squared c. Well, great. Look, a over c is something that we know what we want, cosine of a plus b. And then this term here is sine a times sine b. A times, on the numerator, a times x times y. On the denominator, b times c. Perfect. So that is the sine of a times the sine of b. And yes, fantastic, because this then tells us that the cosine of a plus b is cosine a cosine b take away sine a sine b, which is the other addition formula for the cosine of addition of angles. So there we go. That worked out quite neatly. I wasn't sure I was going to be able to fit all that onto one page, but that is a geometric derivation of the addition formulas for sine and cosine, which I think is nice because it's lots of utilization of things that we learn at the National 5 level. We had to use Pythagoras' theorem multiple times. We used the sine rule, we used the cosine rule, and we were able to finagle our way to these derivations. I suspect there might be slightly slicker geometric derivations available that will have been worked out, but this one is reasonably okay. It's something that I just came up with the other day, and hopefully, you know, kind of interesting for those of you who aren't content just to accept a formula and want to see, where does it come from? Prove it to me. Well, here's a proof. Wonderful. Now, I'm going to pause with trigonometry tutorials and I'm going back to calculus because we're going to use the addition formulas plus our understanding of the radian to look at the calculus of sine and cosine. Fantastic stuff, and I look forward to seeing you for that next tutorial. Bye for now.